Welcome back to the Foundations of General Emergence Mechanics course. We're on episode 11, and honestly, this is where things get really fascinating. We're going to dive right into this explainer and take a pretty massive conceptual step forward in our mathematical journey together. Looking at what we've got lined up today, we're going to trace the path from persistence straight to gravity. We'll explore motion in a mathematical landscape, lay out the minimal math for persistence depth, and really contrast this geometry with traditional forces. We'll also, of course, strictly define the academic limits of what we're claiming. Ultimately, we're exploring how spatial variations in depth naturally produce directed motion, which fundamentally reinterprets gravity within our framework. So let's ground ourselves first. We need to look back at exactly where we left off in the previous modules so we have a solid footing for today's leap. You'll remember in episode 9, we introduced the 3 core axes of our framework. Then in episode 10, we really got into the persistence score, structural imbalance, and failure modes. That was a crucial moment, right? It was when general emergence mechanics became truly operational. And that naturally leads us to ask a pretty profound question today. If persistence actually has geometry, can large-scale motion arise directly from that geometry? What exactly happens when depth isn't uniform across space? Well, the central proposal of today's explainer, the answer to that very question, is that gravity is not some extra force just layered on top of persistence. Instead, gravity is simply the behavior produced when persistence depth is spatially non-uniform. It's fundamentally an emergent property of the landscape itself. To really get a grip on this non-uniformity, we need an intuitive sense of how the environment actually dictates movement. Let's use some simple Bayesian intuition here. If you picture a flat Bayesian landscape, which represents uniform depth, any particle or body placed there has absolutely no preferred depth-driven motion. The geometry is totally indifferent. But if you look at a sloped Bayesian landscape, where depth varies, suddenly, the geometry becomes highly directional. The environment itself begins to gently, but inevitably, guide those trajectories. Because of this, what has historically looked to us like gravitational attraction can simply be read as an object naturally moving toward deeper admissible regions in a non-uniform persistence landscape. Its trajectory just naturally aligns with the steepest persistence descent. It isn't because one object is mysteriously pulling another, it's because the persistence landscape they occupy is fundamentally not flat. Now, to make this mathematically useful and intellectually rigorous, we need to formalize how this landscape actually behaves. Let's start with a clear, plain language definition. A persistence depth potential field is essentially a topographic map of stability in space. So how does this relate to the movement of particles? Well, objects within this field don't need some mysterious, invisible tether to be pulled toward one another. Instead, they simply roll into the deeper valleys of the persistence structure. They naturally seek out the most stable, deepest regions available to them. We can represent this depth conceptually as a schematic field mapping across space, acting as a function of position. Whether we're thinking in purely spatial terms or across space-time coordinates, this field establishes the baseline depth at any given point. And remember, if this field is completely uniform, there is absolutely no preferred drift. But when this field does vary, we look at its mathematical gradient. The gradient measures exactly how and where that depth changes, which establishes a preferred structural direction for any system inside it. It essentially points the way down the slope. And this gives us a minimal teaching law for motion. Conceptually, without getting bogged down reading every symbol on screen, this tells us that an object's acceleration is directly proportional to the negative gradient of the persistence depth potential. In plain, everyday terms, an object will simply accelerate down the steepest slope of this persistence landscape, constantly shifting toward greater depth. This concept brilliantly illustrates the fundamental paradigm shift we are making in the general emergence mechanics framework. We're carefully teaching a vital distinction here. In the standard historical view, masses mysteriously attract one another across empty space. But in the GEM view, matter fundamentally organizes and reshapes the persistence depth landscape around it, and then motion simply follows the resulting gradient of that landscape. Please note, we're not denying observed gravitational behavior. Apples still fall from trees, planets absolutely still orbit stars. We are simply reinterpreting that behavior. We're moving from an external force of attraction into a purely geometrical consequence of persistence. This is a huge unifying step for our framework. Gravity is no longer this external phenomenon that we have to awkwardly bolt onto our equations. Instead, gravity becomes the very first major, large-scale consequence of persistence geometry. It makes motion completely intelligible inside the exact same structural framework we've been building together since episode 1. Now, as with all deep mathematical work, it is absolutely crucial to be honest, patient, and rigorous about what we are currently establishing. So the crucial takeaway here is that this is purely a foundational reinterpretation step. We're laying the groundwork. This means we aren't yet presenting a full coefficient-level replacement for Einstein's equations of general relativity. We're not jumping into detailed cosmology, the expansion of the universe, or the specific mechanics of black holes just yet. Those derivations, they will come later. Today is solely about understanding this one vital conceptual move, gravity as a depth gradient. Let's bring this all together, move to our conclusion, and see how this builds our core understanding of the universe. If we trace the logic sequentially, it's actually quite elegant. First, persistence has a depth. Second, that depth may and does vary spatially. Third, those resulting depth gradients naturally guide motion. And fourth, this yields an entirely new geometric reading of the phenomenon we have historically labeled as gravity. As we close out this explainer, I want to leave you with a rather profound thought to ponder about the very nature of a falling object. When you see an object fall, is it truly being tugged by an invisible force from below? Or is it merely, passively, and beautifully following the steepest admissible route through the geometry of persistent space? If depth is real, then depth gradients are real. And if depth gradients are real, then gravity may be the large-scale motion law of persistence geometry. Next time, we ask whether the constants themselves are also emergent from that same structure.